Good afternoon, everyone, and welcome to our second SPREE seminar of the year. It's a real pleasure to welcome Gianluca Coletti to come and talk to us. So Gianluca actually was one of the first people I met when I came to SPREE. It's a bit like when you turn up at your new job and there's a friendly face down the corridor, and I assumed he worked here. And he is actually an assistant visiting professor here, so that wasn't too much of a bad guess, but then I learned he came from the Netherlands. He works at what was ECN, is now TNO, and he does really lovely work. So Gianluca, we're really excited that you can have been with us for the last couple of weeks and you can give us a nice seminar. So Gianluca's been at TNO since 2004. Before that, he was at a company called Solari in Italy. So Gianluca, thank you, and we're really looking forward to hearing about your work on tandem solar cells.
Thank you. Thank you, Ned. Good afternoon, everyone. Yeah, it's a pleasure to be here and present this result. So today I want to go through the idea of tandem, but the idea of when you combine tandem with bifacial. So first of all, I want to acknowledge our partner, the partner in Solliance, and my co-authors for the work done, and well, a little bit of the outline. So I will start about cost-effective tandem, and for this it means that you don't need to include only the efficiency, but you need to include the energy yield of these devices. So I will start with the concept, what does it mean tandem, what does it mean tandem with bifacial, but also what's the metric to compare tandem with, to compare monofacial with bifacial. And then I will go through the device we made, the simulation of outdoor conditions, and the real outdoor condition data. And then I will conclude with the scale up to large area and the conclusion. So this is the result of the ITRPV that show that already by 2023 there will be a non-negligible market for tandem, and probably already in 2021 start the mass production. Now this is a very good news, but it's also a news that you need to compare with what would be the market by then. So when was it? A couple of years ago, we had a meeting with colleagues. We were trying to put together a proposal for tandem, and we were discussing what should be the efficiency target we put for these devices. And then it was on the trip back from Paris on the train that we think, well, what is going to be the market in that time? And that's what we see here, that also a prediction of the ITRPV, in 2023, the market will have 50% of bifacial cells. Now, those are only cells. You can install still cells in monofacial devices, but why you want to do that? So the idea is that there will be a really large market for bifacial. So essentially, when you design your tandem device, you need to face that, and you need to face the fact that it's not only about efficiency, but it's about energy yield. So this is, of course, for the market segment ground PV and probably commercial rooftop, where bifacial has a role. But then if you can design, and that's already the challenge we see, if you can design a device which is tandem, why don't you directly from the design phase design it with an add-on, which is the bifaciality. So you go from a single junction, normally monofacial. We already see there is a lot of bifacial single junction, and you add another device, but you keep this feature of the rear side, and we will see later why. So those are results. We essentially put together perovskite with silicon. This is a four-terminal device. And our colleague at Solliance made this excellent job. They were able to make single cell perovskite with a very high transparency. And the result here is 17% after 5 minutes at the maximum power point. So we use this as a metric, 17%. Is already a bifacial device, by the way, 96% is very good bifaciality. But the importance here is that you combine the efficiency with the semi-transparency in the near infrared. And then we put that on top of a PERC Plus device. The plus stands for bifacial. It's a device that is 22% and has a bifaciality of 73%, as you see there. Now, when you put this device under the perovskite, part of the light is absorbed by the perovskite, part is transmitted, the near infrared. So the efficiency of the bottom device became 9.2%. Now 9.2%, I think you can see here, 9.2% added to 17 make 26.2. Now this is already something very interesting. You start with a device that is 22 and you can make something in tandem 26.2. This is without any bifaciality yet. Of over 4% on a technology, the silicon technology that is already in mass production. Then we put, let's say, our more advanced device. Here is an heterojunction with back contact. Contact in the rear side is an NWT, which has an efficiency of 22.8%. When you put these under the perovskite, it generates 9.5%. Therefore, in total, you have an efficiency of 26.5, and a bifaciality that is very interesting, 84% on the 84% on the single junction use, and 72% when is filtered with the bottom device. So 26.5 and 72%. Now the question is, those are all bifacial device, but measured in standard time condition with a black rear that block the light to be reflected. Okay, interesting here you get again 3.7% absolute gain respect to the single junction efficiency. But now let's look at the structure of this device. As you see here, you have the perovskite, and that's absorbing, let's say, the blue and the UV and the visible part of the spectrum of the light, and is transparent to the near infrared, and that's absorbed by the silicon device. Now, when you include the effect from the rear side, note the important is that from the rear side you have the full spectrum. So in practice, you can yet design a bottom device that is not so responsive to the UV in the front, but then in the rear side you still want this feature. Now, when we compare this with a monofacial device, that's where I talk about we need to introduce a metric, and here is the metric of we think to use power density that is more meaningful to give idea on how much this device are giving. There is a new norm now on how you measure bifacial device, which define essentially you report the device with 0 irradiance from the rear side, 100 or 200, which is like 10% or 20% of one sun. It's so-called BF 100 or BF 200. So let's say you add 20 milliwatt per square centimeter from the rear side, you measure the power, you divide by the size, so you still have something that might remind an efficiency, but is actually a power density. This is a good metric, I think, and it's a metric you do in the lab. Later I will explain about a metric you use in real simulation. So, but now the question is also, okay, this is 4-terminal, we understand. How do you compare with 2-terminal? Now with 2-terminal, the situation could be a little bit more complicated. Why? Because the two devices are in series, so you have a constraint on the current that pass through them, the same current from the front and the bottom device. Now, since you get more current from the rear device because the albedo, the reflection that come from indeed surfaces around, but also diffuse light like clouds, this create an imbalance. But you can consider this imbalance, and this is what we did in this simulation. My colleagues start to design, first of all, a single junction device. That's what you see here. You add a certain ratio of the light from the rear side. This is 20%, and you see that it's nicely linear. Why? Because it's just a single junction device. When you use the 4-terminal device, the linearity is kept. But of course, you get a higher power density as function of the rear irradiance. And what you expect on the 2-terminal device is that at a certain moment, the power density is capped. Why? Because of the limitation of the current generated in the top device. But you can design differently the top device. You can increase the band gap. You can make it thicker. You can have different modification here. You will still have your capping, but as you see in this case, and consider here we are comparing 1.6 with 1.7 electron volts here. So in this case you generate more power, but then depend on how much is the rear irradiance that would change. So you could design a device that is probably ideal for 10%, 5%, which start to add some complication on the manufacturing point of view, but still it's a gain that come basically for free. So how do this device behave in the bifacial condition? We start, you remember before, there was 23% for the NWT heterojunction, single junction device, and 26.5% for the tandem. These were with zero irradiance from the rear side. If you add the so-called BF 100 or 200, you end up with a power density of 26.8. Now this is important because 26.8 is very close to the 26.5 power density of the monofacial tandem device. So essentially you make a device that yes have more than 4% absolute gain respect to the single junction, but when you compare with a bifacial device, single junction has the same power. So why you do that? You do that because you can have it bifacial too. And then you end up with a power density of over 30 milliwatt per square centimeter. And this is the interesting part, right? So let's move to next. So far we discussed about standard test conditions, so how you can measure in the lab, but how do you compare with a module that actually you put on in a real outdoor test condition. And here is a new metric. Here I call it equivalent efficiency by energy, because it's the energy produced by that particular module. And there is a nice definition here. It's called equivalent efficiency, and note, is the efficiency of the monofacial device required to produce the same energy of the bifacial device, of course, in the same condition. So we will use this in our calculation. This is done with the Big Eye, a software that we developed at TNO a few years ago and was already validated with data in the field. As you see, is a configuration with shed. We use meteorological data from Amsterdam. It's south facing. As you see here, there are 3 rows of module. Each row is made of 2 module eyes in landscape, and their length is the length of equivalent 11 module, 1.6 square meters, so let's say 60 cell standard. The ground clearance is 1 meter, and there is a fixed tilt angle of 37 degrees, which is the optimum for Amsterdam. What we look at the simulation is only from this row. And then we have an albedo, we add an albedo of 30%, we also calculate 20% and so on, and a ground coverage ratio that is variable. But we look only at the result from this module here, so essentially we can compare all the different technology, assuming they have all the same constant total module area. And why we need to model that? Because as you can see, the row here and the row there cause some shading, cause some side effect that you need to consider when you make your simulation. So those are the results for typical Amsterdam data in 1 year. The monofacial single junction NWT produced this amount of energy, and the bifacial we see as something like 20% more. The monofacial tandem a little bit higher, and why it's a little bit higher despite before we saw it has similar efficiency. The reason is that perovskite has a better response in terms of temperature coefficient and sensitivity at low light. That's why in the energy you see that effect larger than only in standard test condition. And then the last one is the bifacial tandem, that we give way much more energy. So here is the real energy, how this convert into this equivalent efficiency. We use as a reference the monofacial NWT silicon heterojunction single junction module. which produce around 23%. And then you need this device to produce, this device efficiency to go up to 26% in order to match the energy yield of the bifacial device. And we need about 27% monofacial single junction device in order to match the same energy yield of the monofacial tandem. But look here, you need more than 30% when you combine tandem and bifacial. Now, this is the first, let's say, indication. A monofacial device, single junction, over 30% is physically not possible. This is just a quick note. And that means that when you want tandem, you need to target at least this 30%, because then you will be above what you can do with the bifacial. So it's, let's say, it's the entry level. These were result of our calculation. Then we need to make minimodules. For doing that, we use perovskite with 6 interconnected cell, 2 by 2 square centimeter. We use the same PERC cell, but we cut it down to the same size of the top device. We encapsulate with glass minimodule. We use a thermoplastic encapsulant, and the assembly is done in normal lab condition, also for the perovskite. We paid special attention to the edges, because that's where moisture can penetrate. So we use silicone kit and aluminum tape to really protect the edges. And we think in this configuration, we should be able to put the device outdoor. But before to do that, okay, this is how the mini modules look like. Before to do that, we wanted to do some preliminary accelerated test, again, to confirm that this device will last enough time in the roof to be measured. So we start with the dump heat 100, 85, and we get 96% of the initial performance. Then we did the thermal shock, and this is more to stress the interconnection, the metallization. And here we obtain we have a 106 initial performance, because the annealing itself did something good in the perovskite. But then we combine now the thermal cycle with the dump heat, which is the worst condition. Why? Because with the thermal cycle, as I said, you stress the interconnection, but also the edges where the terminal come out from the module. And then the dump heat essentially have moisture trying to penetrate. But the good news is that because of this gain we had before, we actually have the same initial performance. So despite this test is not yet at the IC level, it's a first indication that, okay, we can put this device on the roof. And so we did. So you see here on the left side the module in the outdoor configuration. There is somehow concrete on the rear side, and consider the albedo of concrete change, of course, depends on the real color, but it's between 20 and 40%. We expect this to be 30%, which is what we use in the calculation, so to try to see if this result validate our model. This is something important when you do outdoor testing. We have a simultaneous AV tracing of all the modules at the same time. This is important because, okay, especially in the Dutch climate where there are clouds that come and go, you really need to measure all under the same irradiance for easy to compare the result, but that's valid everywhere. So essentially we simultaneously measure all the 6 modules every 10 minutes, and in between we keep both modules at the VMPP. The result that you see here, so you see the IV result, you see the first 100 hours of light, and here we plot the power of each module as function of the front irradiance. You see here the bifacial Four-terminal as function of the monofacial Four-terminal, and the ratio between these two is approximately 20%, which is what we have seen in the calculation, where you have roughly a gain of 20% in the energy generated. That's what gives this equivalent efficiency boost of 20%. So we went further. We measure for longer time, up to 1,000 hours of data collection. Here I report something different. This is the power over the irradiance, but I plot only the irradiance value between 900 and 1100 watt per square meter. So they give an indication on how the performance of the device is stable. So we test two module generation. One is the one you saw before. We tested another one together with the three type of perovskite made in with different material. And you see that for at least two of the configuration, so the match of perovskite and module generation, there is stability for the first 1,000 of hours, while we already see an early onset of degradation in the other. So this is already give an indication which direction we need to take to maintain the stability of the device, and especially how good and the development you need to do when you integrate them into one module. So next is about, let's say, scaling up of this technology. The solar cells, the perovskite cell is a single cell that I show so far, then I show the mini module result. But essentially at Soliance what we do is to design the material and all the layers as a single junction, as a single cell device, and then transfer them to the full module side. And here is a glass sheet of 6 inch, where there is a device of 100 square centimeter, as you see in the picture, used with the same material used for the single cell. So this device produces 13.5% efficiency, 5 minutes at MPPT, and we put that on top of our NWT silicon heterojunction. We obtain 8.1% efficiency point from the bottom device. With the top device you get 21.6. As you see, we didn't achieve back the original efficiency of the single junction device, but this is a much larger area. And we didn't implement here the highly transparent layer that makes the bottom device also boost the efficiency. So in conclusion, we show devices which are bifacial with an efficiency, monofacial efficiency of 26.5%, and they have a bifaciality of 72. The power density in BF200 condition is over 30 milliwatt per square centimeter. The energy yield calculation show that the NWT silicon heterojunction device is needed with over 30% efficiency in order to achieve the same energy yield of the tandem bifacial. And that when you compare the bifacial single junction with the bifacial single junction with the monofacial tandem, the energy yield is very similar. Outdoor data confirm this gain of 20% in the first 100 hours of operation, and then we also show the scaling up to 10 by 10 centimeter with 21.6% efficiency. And with this, I want to thank you for your attention.
Thank you very much, Gianluca. Have we got questions? I'd like to ask a question. Stunned silence. Yes, Gavin.
Very interesting, Gianluca. Thank you very much. On your data where you showed 3 or 4 months, I think it was, of energy yield, the one of the configurations actually went up in the first few weeks, and then leveled off and stayed very stable over the long period of time. What was the reason for the increase in the performance in that?
Well, this has to do with the perovskite. Essentially, we have noticed often that when you do an annealing or when you put them under the light in certain conditions, they improve. And that's what we see. So, but anyhow, we consider stable respect to the initial condition. But it's common. We have seen also at other players that you have this increase. You know, not always.
Okay. Yes, because you said earlier on that that annealing, the damp heat, I think, which condition?
Thermal cycle.
The thermal cycling did give an increase. So does that mean that you'd want to go back and look at that and work out what annealing conditions could give a higher performance for perovskite anyway, and then have a new baseline? Is that something that you're thinking of doing?
Actually, there is now coming out, have you seen the new paper that say how you should measure perovskite in certain condition? And one of the points is also that probably you need to do the right preconditioning before you start. That include also illumination and annealing. Yeah.
I have two questions, mostly technical. Thank you very much for your informative talk. So the first question was, have you continued measuring after the 100 hours to see what happens, or you stopped at the 100 hours? And the other question was, so it's good you mentioned about preconditioning. So these measurements were done without preconditioning? Okay.
Yeah. So we went over 1,000 hours, and actually the module are still on the roof, so we are keep on collecting data, but I expect most of the configuration went down to zero. So the question now is to take them out of the roof and understand the reason why you have that, because you need to separate if reason are more device technology related or encapsulation technology related. And the last question was answered. Okay, yeah.
So you mentioned that you achieved this 20% increase, same as you had predicted using your simulation with Big Eye. But the simulation was done with TMY data, right? With TMY, typical meteorological data.
Yes, yeah.
So how did it compare? How does the TMY compare to those 100 hours where you measured in natural light, in natural conditions? Did you compare that one too?
No, so essentially the 1,000 hours that we register outdoor is in the condition where we have the most variation. So we did it around the Dutch summer, where you can have really low irradiance and very high irradiance, because that's how you see most of the response. And that's where you should get most of the gain, but ideally you want to have at least 1 year, and we have seen that the results are pretty much in line. And actually when we measure in this, let's say, summer condition, you have a very good replica of the rest. If you measure only in the winter, it's not such representative. Yeah.
Thanks for the lovely talk. So just a question about the comparisons between the single junction and the double junction. So your MWT cell is textured, is that correct?
Yeah.
So when you have your tandem device, the perovskite is not textured?
The perovskite is it's on the glass. The bottom device actually is designed the best for single junction, so I expect that one has to be adjusted in order to get the best when it's encapsulated in that way.
Yeah, so the top cell is planar, and then the MWT cell is still textured. Okay, and so optimally, that's not really
right. Is not the optimum from the light management point of view, right?
Because I think Kylie's work has shown that the perovskite cell needs to be textured.
Yeah, I expect so.
Okay.
Can you talk about the test conditions for a bifacial cell? You know, the spectrum coming from the sun is the spectrum coming, you know, you can have a reference spectrum or it's whatever, it's from the sun, but, you know, it would seem to me that the specifics of the ground make a big difference here. So can you talk about that a bit?
Yeah, it makes a difference, and depends on the surface make a difference. You can find the literature data that show that shift is not a huge shift, so much that in most conditions you are below the error that you have anyhow in the measurement, but this is something really important. So in a follow-up publication we are including this effect, which can be marginal, but you know, when you calculate the energy yield, can start to become important.
So is asphalt similar to dirt and similar to grass?
It's all different. Yes. Yeah.
So does it have a big effect?
It doesn't have a huge effect, especially if you consider which part of the device. Like we would see in the bottom device, you wouldn't see, because the EQE of the bottom device is nearly flat around all that range, so you don't expect much change. It's something to consider when you want to be accurate, and it's something that actually we are implementing, but we don't have yet.
So as you change the conditions, you're saying you wouldn't necessarily change how you'd measure it. You might get a lower total intensity if you have less reflection.
If it's just shift, not, and it depends on the spectral response of your device, bottom device in this case, where you see for silicon is it's pretty flat in all that range. Actually, it could be also beneficial because you have a cut on the UV, which is normally not used.
Yes.
Yeah. Thank you for your talk. Very impressive results that you have the mini module and you have the outdoor testing already of these tandem devices. I was wondering, so you have damp heat tests on a mini module setting. I was wondering if you'd looked at PID for the bifacial tandem cells, particularly because bifacial is more susceptible to PID potential induced degradation problems.
Yeah, that's a good question. And the PID, honestly, I would be more afraid on the perovskite side than on the silicon side, because on the silicon side you can address that the same way you address in a single junction device. It's something to be tested, definitely on the tandem, definitely on the perovskite as well.
Any final questions? Yes.
If we can optimize the surrounding condition, would this four-terminal bifacial give the highest power density per area, comparing to if we can optimize the albedo? Let's say we have a limited rooftop space and I want to generate most amount of power, then
yeah, so that's what you see when you change the ground coverage ratio, which means the distance, the pitch, the distance between modules. So if you want to have the most power, actually you put them the farthest apart, because then you have more of the effect of the albedo. If you have a constrained surface, you need to optimize that in a way that you get the most of the most, but it's also depending on what you want at the end. So for a commercial rooftop, and you really need to match the power that is needed or the energy that is needed to run the business, you might have a different consideration that if you want to just optimize the cost, for example, the total cost of the investment. But it's true, the more you put them apart, the more albedo you have. You can even add or paint the bottom surface to increase the albedo. And here to have more of a figure of merit, if you have an albedo of a certain amount, you have an energy yield of roughly half of that amount. So for 30% you have an increase of 15%, 17%. But it depends also from location to location. So in the paper we are writing now, we compare Amsterdam with Denver, that there is a different diffuse light, and so the bifaciality is much better when you have diffuse light than when you have direct light. So this change cannot have a one rule for all. Yeah.
Okay. No more questions. In that case, I'd like to thank Gianluca again for being our talk. Thank you.
Thank you.